Okay, following up on the linear algebra question collection that I had, in question E, when I was explaining, I was saying that Vincent told me there's a better way to do it. I don't exactly remember which way. I think he was talking about the third way here, but definitely I did learn some new things from here. So first is compute a non-singular matrix P and a diagonal matrix D such that A equals P inverse dP. So basically inside here, last time I wasn't sure how to do P, how to get from my P to my inverse quickly. What I did, my approach earlier was I just basically just found the inverse the hard way of like finding the determinant, putting that on the denominator, then switching up my terms, and then negating it using the 2 times 2 formula. That was what I did. But for n times n, that might not exactly work out. So instead, some other approaches I found were the following. The first approach is noticing that actually the thing is symmetric because we see that our A is a symmetric matrix, so we know that its eigenvectors are actually orthogonal. So what we can do is the idea is that we can normalize the eigenvectors to have length 1. So then that way that would be an orthogonal matrix. And a special property of orthogonal matrix is that the inverse is the transpose. So then that would save a lot of calculation. But unfortunately, in this case, because we have the numbers don't aren't quite nice, it is quite bothersome to do the calculation this way. When we calculate the length, we have to normalize it to 1. So that would make the square root appear. And then when we normalize it, we get this because there's a square root to keep that. And now when we transposing is easy, so we just change it up, change the rows and columns. So, well, this method is really useful most of the time. It's actually a really unique way of seeing the problem. But in this case, because we have a irregular number, it's kind of like regularizing it to one, normalizing it to one is kind of sad. The other like typical approach that I didn't use, but that would have been helpful for n times n when I have no idea how to do it, is just to use the Gaussian elimination method. So basically what I start off with is I just keep the I over here, do the row reducing so that I get to what I need. So then I would get what I need. That's a pretty basic approach, but it's doable for sure. And then the third approach, I think, is the nicest because we take advantage of a property that we have like A, P inverse dP. So we can just think of multiplying P at the front of the equation. So then we get PA is equal to dP. So then that's a very nice equation, right? So then we can say that we know it's a 2 times 2, so we write the rows of P. If it was n, it's expandable as well. So then we have R1A is equal to the golden ratio R1. R2A is equal to the other root, R2. So then we realize that it's the left eigenvectors of A. So then here we know that there's a trick. There's a symmetric matrix. The left eigenvectors are the transpose of the right eigenvectors. So then basically what we know is whatever our eigenvectors were before, we just put them into transpose it and we get what we need. And then we can write it in this form. The matrix is this form. This is very easy. So we just put it in. We just do a dot product to make sure whatever our coefficient is, we know we find the coefficient. And then we get the coefficient is this thing. So we get back to the same thing we get. No matter which method we use, we get the same answer. But I say inside this case, the simplest one and the most expandable one for n times n matrices is definitely approach 3 because it's expandable and it's really easy to calculate. Okay, let's end it off here.